Okay, so Shahid, are you all set up? It looks like you're screen sharing already.
I'm ready.
Okay, great.
Okay, our next speaker is Shahid Sharif. He's going to talk to us about quantum money from Quaternion algebras.
Thanks, Travis. Thanks to the organizers for putting on this conference. All of what I'm going to be talking about is joint work with Daniel Kane and Alice Silverberg, and is based on some earlier work of Daniel Kane from a few years ago. So first of all, let me talk about what quantum money is. Because of cryptocurrency, because it sort of sucks a lot of the oxygen out of the room, a lot of people immediately, what springs to mind is the kind of functionality that cryptocurrency provides. But quantum money is a totally separate object. It's money, just concretely, it's money which consists of both quantum and classical data. But really, you want to think of it as a drop-in replacement for paper money, not as some kind of digital money that has some sort of privacy guarantees. The main motivation behind it is an observation by Wiesner in 1983, and Travis from the previous talk mentioned the no cloning theorem. Wiesner observed that you could use this no cloning theorem to come up with money that potentially would be very difficult to counterfeit. So that's really the motivation behind quantum money. So let me be a bit more precise. Quantum money protocol consists of three things. The first is a specification for what the money actually looks like. And I already said it consists of both some quantum data and some classical data. So I like to think of this physically as being something like a credit card with two little chips in it. And one of them is a regular chip that contains some classical data, and the other one is a quantum chip. I don't know what that'll look like in the future, but something that contains the quantum data. Then we have a minting algorithm, which allows you to produce bills, but you only want the authority who normally produces fiat money, so let's say the Treasury Department in our case, to have access to this algorithm. So it's a private algorithm that will produce valid quantum bills. But we would also like the general public to be able to verify that, in fact, a given quantum banknote is in fact valid. So we have a verify algorithm which allows you to that allows the general public to authenticate whether a quantum bill is valid or not. Okay, so that's what quantum money protocol is. The security that we want is this anti-counterfeiting security, that if an adversary has access to a bunch of bills, valid bills, that they cannot produce additional valid bills. So we'll say a quantum money protocol secures if this is not possible. So just a little overview of existing proposals. So the first public, so I guess what I should say is this is what I'm describing is really public key quantum money. There are other quantum money proposals. But in terms of public key quantum money, the first one was proposed by Aronson in 2009, followed up by Aronson Cristiano in 2012. Both of those were broken. Also in 2012, Farid, Gossett, Hasidim, Litomirsky, and Shor proposed a quantum money protocol that is based on knot theory. There are some issues with they don't have a security proof, but that one is so far unbroken. So it'd be interesting if anyone knows knot theory to see how that pans out. In 2019, Jandry proposed in his quantum lightning paper another proposal, and that was broken a year afterwards, I believe. In that same paper, Jandry proposed a fix to the Aronson-Cristiano scheme in 2012. That fix required indistinguishability obfuscation. Okay, so Travis gave a nice overview of quantum computing. I'm going to do the same thing. So there'll be a bit of overlap with his approach. So I'm going to let little m be the number of qubits. So if you're familiar with classical computing, you know what bits are. So this is the quantum analog. We don't want too many of them or the computation becomes too big. Capital M will be roughly 2 to the little m. And I'm going to let V be the capital M dimensional complex vector space with the usual permission inner product. Then I'll write using the physicist notation, this ket notation. I'll write ket rho to denote a unit vector in our vector space, and I'll call that a quantum state. So whenever you see this ket notation, this vertical line and this angle bracket, that will always mean a unit vector and always denotes a quantum state. If I put an integer between 0 and dimension -1 inside this ket, that means it's that corresponding standard basis vector. I'll let capital U be an m by m unitary, and capital U will always denote that. Then when we have this, a quantum computation is just the computation of a product of this form. You apply U to the first standard basis vector, the 0th standard basis vector. Okay, so one major difference between quantum computation and classical computation is that if you have a quantum state, this is essentially your quantum version of data. You can't actually look inside it. So it's a vector, but you can't actually examine the entries and say, oh, what's the 3rd coordinate? What's the 5th coordinate? Instead, we have this thing called phase estimation. And the input of this phase estimation procedure is a unitary matrix and a quantum state. And the output is going to be a random eigenvector eigenvalue pair, where I'm talking about eigenvectors, eigenvalues for the unitary operator U. The way it works is follows. You pick an orthonormal eigenbasis for U. You write your quantum state in terms of that eigenbasis with coefficients, as I have written here, alpha I. And then we're going to pick one of these eigenbasis elements randomly, and the probability that's chosen is exactly equal to the norm squared of that corresponding coefficient. So because rho is a unit vector and this is an orthonormal list of vectors, the psi i's, the sum of the squares of the alpha i's is going to be 1. So this is consistent with the way probability is supposed to work. And then we replace our input quantum state rho with the psi I. So our original quantum state sort of gets destroyed. It gets replaced. So we can't really extract additional information from the same quantum state. On the other hand, the fact that we replace rho means that the phase estimation procedure is idempotent. If you do apply it twice, you're just going to get the same thing the second time as the first time, because if you start, or equivalently, because if you start with an eigenvector, you're going to end up with the same eigenvector. Here I've suppressed the eigenvalue, but the eigenvalue is also part of the output. Okay, and then Travis also mentioned the no cloning theorem. Here it is. It's very innocuous. So from a mathematical perspective, there's nothing to it. From a physics perspective, this really tells you that you can't copy data. So if rho is the quantum data that you'd like to copy, oops, pardon me. If rho is the quantum data that you'd like to copy, you think of on the left-hand side, the 0 as being a blank slate. And on the right-hand side, you've copied it over into that blank register. So now you have 2 copies. So this is not really allowed. Okay, so and so that's the whole idea behind the quantum money. If that's your quantum data, then you can't make a second copy of it, and that's supposed to be the idea behind. Oh well, this is going to be hard to counterfeit. So our proposal for quantum money. Let me give the generic version first. So as part of the setup, we first choose T commuting unitaries that possess a real eigenbasis, U1 through UT. And quantum bills consist of triples of this form. So psi tensor psi, lambda, and sigma, where psi is a joint eigenstate of the UI. So because these are commuting matrices, there is a joint eigenbasis. So we pick an eigenvector and take its tensor product with itself. That'll be the quantum part of the bill. And then the classical part of the bill are these the lambda and the sigma. The lambda is just the vector of eigenvalues. So lambda 1 would be the eigenvalue of psi with respect to U1 and so forth. And then sigma is just a digital signature for that vector of eigenvalues. Okay, so that's the specification for what the quantum banknotes look like. The minting algorithm is as follows. We first construct this quantum state, which is the sum over all the j's of J tensor J. So remember, this is the notation for the Jth standard basis vector. And then we apply the phase estimation method to this row with U1 tensor I. And then you repeat this with the remaining U's. And the reason that this works is because the sum of J tensor J equals the sum of psi J tensor psi J, where the psi J are a real orthonormal eigenbasis, joint eigenbasis for the U's. So when you apply this phase estimation procedure, you'll get one of the summands on the right-hand side, and the one that you get will be chosen with uniform probability. So they're all equally likely. So that gives you the psi tensor psi, the first part of the quantum bill. And then the phase estimation also gives you the eigenvalue. So that gives you the vector lambda. So now you just digitally sign that tuple, and that gives you the sigma. Of course, the digital signature algorithm, that requires access to the signing key, which is a private key. And that's what makes this minting algorithm a private algorithm. Okay, that leaves the verification. So this is supposed to be a public algorithm. So we have our unitaries, and then we have a quantum bill. How do you check that it's actually valid? So you just apply the phase estimation procedure again. If rho is in fact of the form psi j tensor psi j, or psi k tensor psi k, let's say, then that's going to be an eigenvector of uj tensor I and also of I tensor uj for all j. And so the phase estimation procedure will preserve that quantum state. But it'll also, the phase estimation procedure will also give you the eigenvalues, so you can actually check that the lambda is correct. And then you just check that the digital signature is correct as well. And anyone can do this, so this is a public algorithm. Okay, so for security, so I mentioned that we want to make sure that counterfeiting is not possible. We reduce to the following security problem, which is a triplicate eigenstate problem. Given the commuting unitaries, can you produce a triple tensor product of an eigenstate with itself? So in the minting procedure, we actually produce a double tensor, but somehow producing a triple tensor is much harder than producing a double tensor. And that's really what the security boils down to. So we show that the security depends on this problem. And then we prove that if an adversary has only black box access to the unitary matrices, to the unitary operators, then there's no efficient algorithm that can solve the security problem. And therefore, putting it all together, the black box protocol for this quantum money is unconditionally secure. So I'll put this is the formal statement of our theorem. So you have a quantum circuit that has decontrolled uj gates. So here I'm thinking of uj as being black boxes. So in a classical algorithm, you could say that we're making d calls to uj's as oracles. And then the u's are going to vary randomly in some way. And so we'd like to see what is the probability that our quantum circuit can solve the security problem. And we give this expression for the probability in terms of the number of queries to the uj. If the number of queries d is polynomial in log n, then this probability will be a negligible probability, which gives us the security that we want. Okay, so that was the generic protocol, but we have to have an actual instantiation. So what we use for our instantiation, just briefly, is just we take Brandt matrices and take exponentials of the Brandt matrices. So now let me explain what that is. So this is not the long version. The long version is too long for a talk. But the longer version is we choose capital N to be a large prime. We take B to be the quaternion algebra ramified at capital N at infinity. So for instance, if capital N is congruent to 3 mod 4, then this quaternion algebra looks like this. So it's as a vector space, it's 4-dimensional over Q, generated by 1, I, J, and K. And we have these multiplicative relations. I squared is -n, J squared equals -1, Ij is equal to K, and Ji is equal to -ij. Then you pick maximal order in B. So this is a ring, a subring of B, which is maximal for the property that it is finite as a Z module. So it'll be rank 4. And then CLS of O is the left class set of O. So it's not so this is like the class group, but if it's because we have this, we're in a quaternion algebra, it's not going to be a group, it'll just be a set. So it's just going to be the set of left ideals of O under essentially the equivalence that you would think it would be for class groups, except we only allow multiplication on the right to give equivalence. V is going to be the vector space whose basis elements are exactly the ideal classes in the class set. And then we're going to pick a set of T small primes, P1 through PT. And then we have this thing called a Brandt operator. So for each prime, a small prime P that we've chosen, the associated Brandt operator takes an ideal class to a formal sum of other ideal classes. And it's essentially ideal classes so that there are representatives which have index P inside the starting ideal class. So these Brandt operators, they're self-adjoint for an appropriate inner product. So when you take a self-adjoint matrix and take a complex exponential, so e to the I tj, that gives you a unitary matrix. And so those are going to be our unitary matrices. The Brandt operators are commute with each other, and therefore the unitaries are also going to commute with each other. Okay, so I didn't really give that detailed an explanation of the Brandt matrices. So let me give a couple alternate characterizations that you may be more familiar with. The first one, the more number theoretic one, is the T of P. So for the small prime little p, it is the Hecke operator acting on weight 2 cusp forms of level n. So in other words, the vector space V is isomorphic to the space of weight 2 cusp forms of level n, and then the Brandt operator acts like the corresponding Hecke operator. And then the second characterization, which probably is familiar to most of you, is if you take the set of supersingular J invariants in characteristic capital N and look at the P isogeny graph, then T of P is just the adjacency matrix for that P isogeny graph. So in a sense, this is actually the better characterization, because up to reordering of your basis elements, this will literally give you the same matrix. So in the Hecke operator case, you have to pick a basis first, and it's unclear what basis to pick to get the right matrix that we use. Okay, so now let me talk a little bit about some open problems related to the security of the scheme. So the first one has to do with randomness. So we would essentially just like that our operators, the UJs, that they're both the eigenvalues and the eigenvectors act somehow randomly. So we do have some information about the eigenvalues. Sayre in 97, I believed, showed that the eigenvalues of these normalized Brandt operators are distributed according to this measure. So they, in the limit, as capital N goes to infinity, if you fix little p, the eigenvalues approach this limit. And in fact, he showed more than that. He showed that if you give, as we do in our setup, have t primes, p1 through pt, and look at the joint distribution of the eigenvalues, that they are independent and approach the product distribution. But unfortunately, that's not enough. We really would like those eigenvalues to really act randomly. And so the question that we'd like to know the answer to is, are the eigenvalues actually indistinguishable? I wrote distinguishable here, but same question really. Are they distinguishable from random from a computational standpoint? So you can think of this in the following more formal sense. If you let capital N be really large and you pick up small prime p, and then I take just a few of the eigenvalues of T of P, so polynomial in the log of n. And then I also give you some random numbers that follow the same distribution that Sayre's theorem describes. Can you tell them apart? And hopefully the answer is no, but I have no idea. As for the eigenbasis is even harder. I don't think there's any results known about this. But if the eigenbasis, for instance, is very predictable, then it's very easy to counterfeit money, because maybe you can predict, oh, I know that this particular vector is going to be an eigenvector or is very likely to be an eigenvector. And then maybe you can just manufacture it directly and then manufacture 3 copies, and that gives you a solution to the security problem. So here I mean in the representation that we use with Quaternion algebras. So you could instead use the supersingular elliptic curve representation. That's harder to compute with, but it at least amounts to the same question. So in that representation, is there some pattern to the way the eigenvectors look, or is it really just you can't tell it from a random or orthogonal basis? There's another attack. So in the quantum realm, this is called quantum state restoration. If you can write one of these mystery eigenvectors as a tensor product of 2 other vectors, then you can do like a dimension reduction attack and try to copy V and W individually. But of course, in order for this to work, you have to be able to write your joint eigenvector in this form. So here our given eigenvector is psi, and we'd like to be able to write it in the form V tensor W. So this may not be possible, and even if it is, can you come up with it? So the question is, for our particular instantiation, is there an efficiently computable way to come up with such a decomposition, even part of the time? There's some other open problems in the paper, which I invite you to check out. But otherwise, thank you so much.
All right, are there any questions for the speaker? Kate has a question.
You have a slide, a couple slides back. Oh, we lost you.
I'll put it back up. Okay.
Yeah, a couple slides back, you mentioned the distribution of SER.
Yes.
And you had a couple questions after that, 1 and 2 there. And I'm just wondering if anybody's done numerical experiments, if there's data or evidence for these.
Yeah, that's a great question. So there have been additional results. Let's see, there's Murthy and Sinha have some additional results. And I just talked to somebody, Zubralina and Sarnak, I think, have some additional results. But they're all asymptotics in terms of like how good is Serre's estimate. So I have no idea what the data would look like that would tell you whether it's distinguishable from random. So yeah, so people have generated data, but just looking at the data, I don't even know what you would look for to tell. So yeah, so I guess I would answer, I don't really know. So yes, but in regards to this question, I don't know.
There's another question.
Yeah, I had a question about this slide as well. So forgive me if I'm missing something, but is the question whether the eigenvalues are distinguishable from like randomly sampling from the distribution that like independently randomly sampling from Serre's distribution, or is the question whether Serre's distribution is like distinguishable from something else? Like,
no, it's the first one.
Okay. So the eigenvalues may not actually be independent, and like to what degree is that detectable?
Yeah, I mean, so it's even stronger. I mean, there can be even worse behavior than not being independent. Well, I guess it depends on what you mean by independent, but yeah, there could be certain patterns in the way that the eigenvalues occur. So they could be like very evenly spaced, for instance, right? And they would still follow distribution. But then you would be able to detect them. You'd say, oh, well, like, they repel each other, so therefore I know that this random one where there's some more clustering is the actual random one and not the Serre distribution. Or I'm sorry,
Okay.
the distribution of eigenvalues.
Okay.
Yeah, it's
As
kind
in,
of
thank you.
weird. I mean, I to be honest, I don't really understand randomness and these like questions of like what is random, how random is something. So this also really puzzled me when I came across this idea that yeah, we know the SARE result, but that doesn't actually guarantee randomness in the computational sense. So it's possible that I mean, if you think of like the digits of pi, you can easily compute them, right? You can't really predict them. So the question is, can you predict something about the eigenvalues? Uh, uh,
Hmm.
and if you can do that kind of prediction, so this is sort of like an information theoretic question, then that could possibly enable an attack.
Okay, thank you.
Well,
Any more questions? Yeah, one in the back. If you'd like to.
Earlier on in your talk, you gave a result on your generic version about like unconditional security. And I was wondering if you needed this randomness in your concrete instantiation to be able to apply this result, or if you needed it for sort of to mitigate other possible attacks, or I was just wondering why can't you apply this result on your instantiation that you have?
yeah. Why can't we apply this result? Because, yeah, I mean, I guess I would say essentially because we don't know that they're random. So this result, the theorem, yeah. So the theorem, let me say a little bit about the randomness in this theorem. So I wrote this as suitably random tuple of commuting unitaries. So the way we generate these unitaries is we choose a real eigenbasis completely randomly, so that uniformly at random. And then we choose the corresponding eigenvalues. And that one, you basically can choose any distribution as long as choosing the same eigenvalue has probability twice has probability 0. So for instance, you could use Serre's distribution, or you could use some sort of uniform distribution. Because we don't know that, right, because the Brandt operators, they are deterministic. You can't actually compute them. So that's essentially part of the question. Do they act randomly enough that they fall under the rubric of this theorem? And I guess I'll tell you, in terms of the eigenvalues, I think probably the answer is yes. I don't have a ton of intuition about it. For the eigenvectors, I think that's really the problem, because the Brandt matrices are sparse. So I think if you pick a random eigenbasis, you're not going to get the exponentials to be sparse. That should happen with 0 probability. So I mean, in terms of like the actual rigorous formal proof, this theorem just doesn't apply because the Brandt operators aren't literally random. In terms of like why, I mean, I hope that this theorem also applies to the Brandt operators in principle, but because we don't have these randomness results for the eigenvalues and eigenbasis, we can't literally apply the theorem. Does that answer your question?
Yeah, it does. Thank you.
Okay.
Any further questions? Okay, maybe I'll end with a lighter one. Do I need to worry about like a quantum RFID scanner wiping out all my quantum money, or
yes, you do. If we do quantum money, I mean, I don't know. Yeah, so you could delete the classical part because you need the digital signature given by the Treasury Department to guarantee that the bill is let me see, where is it?
I think you passed it.
Yeah, here it is. Yeah. So you need the digital signature. So if someone wipes out the digital part of the data, you're already in trouble here. But with paper money, someone can already rip up a bill. So it's not as if we don't have that problem nowadays.
Well, thank you for the great talk. Let's thank our speaker one more time.